our previous example showed us one of the shortcuts that we could possibly take to lessen the burden in evaluating a definite integral, right? Not always having to rewrite it as the limit of a Riemann sum. If there is a geometric formula that you can use, definitely use it. So here are a couple of more sort of shortcuts, maybe. All right, it might come up. Here's the first one. If f is defined at x equals a, then the definite integral from a to a of f of x dx is equal to 0. All right, well, here's one way to think of this. If we're talking about the area underneath a curve, if we're talking about what a definite integral is supposed to give us, if we start at A and we end at A, we don't go anywhere, how much area do we have? A whole bunch of none. Here's another way to think of that. So this delta x that's right here, of course, this dx, I should say, it came from, before we took the limit, it came from delta x is equal to b minus a over n. It's just that our b here is another a. So this is our original a, and then here's where our b value would normally be. So this is an a minus an a, which of course is 0 over some positive number for n, which is equal to 0. We would be multiplying our function times 0 every single time. So of course, the limit of that function should actually, the limit of that Riemann sum should total up to 0. All right, and we've got ourselves another one here, the second one. If f is integrable on the closed interval from a to b, then the definite integral from b to a, wait a minute, that's backwards, of f of x dx is equal to the opposite of the integral from a to b of f of x dx. So what this next one here in green is telling us is if our limits of integration here are in the wrong order, because remember this is supposed to be the small number and this is the big number here. If they're in the wrong order, what we need to do is we switch them, and the act of switching them is going to negate the whole entire value of the integral. To see why that happens, let's think about this real quick here, shall we? All right, so here's this one. Let's switch to maybe some sort of green color. That looks good. So our dx, that's right there, again, came from delta x before we took the limit, which is our b minus a over our n. But if we switch the order of these two things, I can do that by just let's say I factor out a negative from this. So if I factor out a negative, negative b plus a over n, and then I can go ahead and switch the order of those things. I have negative a minus b over n. And so you can see clearly here that if I switch the order of these two, the b and the a, all it does is negates, it puts a negative sign in front of our delta x, our widths, so we're multiplying all of our little rectangle heights by a negative number, so our overall definite integral is just going to be the opposite of the original one, okay? And this could come up, it could come up pretty frequently on the free response questions where I have something that's in the wrong order, so I just handle that by just flipping the order back to what is proper and then throwing a negative sign out in front of it. Okay, I've got a couple of examples that apply this principle. I have the definite integral from pi to pi of sine of x dx. And we haven't taken any kind of limits or Riemann sums of a trig function, but you know what? It doesn't even matter in this particular case because we're going from pi to pi, and the sine of pi is definitely defined. So this is just equal to a whole lot of nothing. Yay! All right, guess how many of those are going to be on the AP exam? Probably 13 of them. All right, let's look at number 2. We have the definite integral from 1 to negative 2 of 2x dx. Okay, notice that these things are in the improper order. The small one's supposed to be down here, the big one is supposed to be here. So I fix that by bringing out the negative sign, switching the order from negative 2 to 1 of 2x dx. And you might recognize this as the example that we solved right up here with that triangle business, which was equal to negative 3. All right, nice. So our answer should be equal to negative 3, or just 3.